Hello friends, in this video we are going to see how the Hall voltage or why the Hall voltage will be developed inside a semiconductor material. So, according to the Hall effect or Hall voltage, we know that a voltage will be induced inside the semiconductor material in the transverse direction of applied current and magnetic direction. For this, let us denote the magnetic field as B vector and the current as Y. Now, both this magnetic field and the current are in the transverse direction. So, if I have applied the magnetic field in this direction B, that is the Y direction, and if the current is flowing in the x direction like this, then a Hall voltage will be developed in this z direction. So, z direction is the Hall voltage induction direction, and this effect is called the Hall effect. So, for this let us take a figure like this, and in this figure you can see that a current, it is a 3D structure of a semiconductor, and where this is the x direction, this is the y direction, and this is the z direction. As we have told earlier that in the x direction current I is flowing, so current I is flowing in the x axis direction, positive x axis direction, and there is an applied transverse magnetic field in the applied y direction or positive y direction. So, a Hall voltage will be developed in between this plane and this plane. So, we will get a voltage in between these 2 points, and this voltage point A and point B. So, we will get a voltage between point A and B as VAB, which will be called as the Hall voltage. Now, why this Hall voltage has been developed? To look at this, let us first see the basics of cross product. So, if we have a value of vector y which is A cross B, where A is any arbitrary vector and B is also any arbitrary vector. Now, we know that according to the cross formula, it will be mod of A into mod of B into sin theta. Now, if I denote this mathematical operation in a graphical approach, then we can say if this is the A vector and if this is the B vector, then the angle between A and B in this direction is theta, and the A cross B will be found as in the perpendicular direction upward. So, this will be the value of A cross B. that is the y vector. Now, if the direction of A and B has been changed like this way, if this is the A vector and if this is the B vector, now the theta direction has been changed in the clockwise direction. So, it is the theta. Now, if we do the A cross B, then we will found that the A cross B will be in the downward z direction. So, this is the basic of the cross product. Now, using this cross product, we will try to explain this Hall effect. Now, after this cross product, we need to know what is the Lorentz force. So, Lorentz force is that force which will be applied on the charged particles due to the electric field and magnetic field. Now, we can say that it is the force on the electric charges due to the presence of both magnetic and electric fields, that is electromagnetic fields. Now, suppose let us take a charge q. Suppose this is the charge q that has been placed in an electric field capital E. Now, the force on this charge q due to this electric field will be q into E in the direction of the electric field, and this force QE is the Lorentz force acting on the charged particle Q due to the electric field. Similarly, if we place a plus Q charge or Q charge in a magnetic field, then it will have some force from the magnetic field. So, let us assume that a charge Q has been placed in a magnetic field and it is moving in the direction like this way, where v is the velocity of the particle, charged particle. Now, the magnetic field direction is in the transverse direction to this field. So, the direction or the angle between V and B is theta in the anti-clockwise direction. So, the magnetic field will give a force on the moving charge Q, and if I denote it as Fb due to the magnetic field, it will be Q into V cross B, where V is the velocity of the particle and B is the magnetic field that is present in the theta direction to the velocity of the particle. So, from this equation we can write that Q into V mod B mod and sin theta. So, the direction of the Fb force will be in the perpendicularly upward direction FB vector. Now, this is the Lorentz force due to the magnetic field, and the total Lorentz force can also be found. So, before that, if I change the direction of velocity and magnetic field in this fashion, that the plus q charge is moving in this direction and the magnetic field is present in this direction, and here the theta is in the clockwise direction. For this case, the magnetic force given on the charge q FB will be downwards along the z axis. So, this will be the magnetic force downwards in the z axis. Now, the total force F total can be written as force due to the electric field plus force due to the magnetic field. And we know that the force due to the electric field is equals to Q into the external electric field that is present, and Q into the velocity of the particle into the present magnetic field. So, this equation gives us the total Lorentz force equation for a charged particle present in the electromagnetic field. With this help of this Lorentz force, we can explain why there is a voltage has been developed in the semiconductor in the previous case. So, let us use this Lorentz force phenomena to describe the Hall effect. For that, let us go to the previous diagram. So, this was our previous diagram where current I is flowing in the direction of positive x axis and a magnetic field is directed in the positive y axis, and a voltage drop will be developed in the z direction. So, if we assume that this is a p type semiconductor, then we know that there will be lots of holes inside this semiconductor, and the holes are like this. Now, when the current is flowing through the semiconductor, that means the holes are moving in this direction. Holes are moving in this direction because these holes will carry the current inside the semiconductor from this plane to this plane. So, let us assume that they have some velocity v during the movement from due to the current. So, an electric field is there in between this point and point. Now, due to the current is moving in the positive x axis, so the velocity direction of the holes will also be in the positive x axis. That means we are getting a velocity of the holes in the positive x axis of the holes, that is denoted as Vx, and we can see that there is a voltage applied in the positive y axis direction, that is in the transverse direction. So, this is the direction of magnetic field that has been present inside the semiconductor. Now, according to the Lorentz law, we can say that these holes that are traveling with the velocity of Vx will experience a force in the downward direction, because the theta is now in the clockwise direction. That means these holes will now experience a force in the negative z direction. That is why we can say holes will experience a force in negative z direction. Due to this, the movement of the holes will not be a straight line, rather than they will move in this fashion. They will tend to move in this direction. So, the holes will accumulate in this lower plane. So, there will be a accumulation of holes in the lower plane, and the movement of the whole direction will be like this. They are not moving in the straight line path. They will tend to move downwards toward the down plane. That means there will be a lot of concentration of holes in the downward plane, and there will be a lesser amount of concentration of holes in the upward plane. So, in this upward plane, concentration of holes will be less, and here the concentration of holes will be high. That is why a positive polarity will be developed here and a negative polarity will be developed here. So, we will get a voltage across this A and B terminal. That means, if we connect voltmeter in this fashion, then we will get a voltage here, and this voltage will be given as the Hall voltage. So, this is how the Hall voltage will be developed inside the p-type semiconductor. Similarly, Hall voltage will be also developed if this semiconductor is an n-type, but the polarity of the Hall voltage will be changed. So, let us look what will be the polarity of the Hall voltage that will be developed inside an n-type semiconductor. So, for that, let us take a semiconductor of n-type. So, this is an n-type semiconductor where the current is flowing out of the semiconductor in the positive x-axis direction, and current is flowing inside the semiconductor in the direction of positive x direction, and a transverse magnetic field has been applied in the positive y direction, and there will be lots of electrons inside the n-type semiconductor, and they will take the current from this point to this point. So, they will have a velocity in this direction, but due to the presence of this magnetic field, a force will be created due to the Lorentz law, and the direction of the force will be like this, because the velocity of the electrons is in the positive x direction and the magnetic field direction is in the y direction like this. So, this will be the theta between Vx and beta. So, the force direction will be in the negative z axis direction. So, this is the Fb force on the electron. That is why the electron will tends to move downwards. So, there will be a lot of concentration of electron in the bottom plane, but there will be less concentration of electrons in the up plane. So, if we connect a voltmeter here, then we can see that there in this point we will get a negative potential, and at this point we will get a positive potential, because the electron concentration in the bottom plane will be higher than the electron concentration in the upward plane. That is why we will get a potential voltage of Vh at this voltmeter, and this is the Hall voltage that will be developed in the N type. But you can look, the direction of the Hall voltage has been changed. Here in the P type it was positive, now it has been negative. So, we will say, so by seeing the polarity of the Hall voltage, we can recognize whether the semiconductor is N type or P type. Now, this Hall voltage will have a value of this amount Vh, that is the Hall voltage. This will be written as beta B I by rho into W, where beta is the magnetic field that has been present and I is the current flowing through the semiconductor. W is the width of the semiconductor bar. So, the width will be like this. This is the width W and the thickness is D. So, width of the semiconductor bar and rho is the charge density inside the semiconductor. Now, this 1 by rho, that is, we can write this equation as B I by W, that is, this 1 by rho is nothing called as the Hall coefficient RH of the semiconductor. So, we can write it as RH into Bi by W. So, this is the equation that will give the Hall voltage of the semiconductor, and RH is the Hall coefficient of the semiconductor. Now, if we know the conductivity, that is sigma, if this conductivity is known for an semiconductor material, then we can find the mobility of the charge carriers is equals to sigma into RH, where mu is the mobility and RH is the Hall coefficient of the semiconductor. Now, so far we have assumed that the charged particles are moving in an particular direction, but generally the charge carrier inside a semiconductor cannot move in a particular directions, rather than they move in a Brownian random fashion. So, if we consider that the charged particles are moving in a Brownian motion pattern, then for the charged particles, if moving in Brownian random manner, then the RH value will be different. So, the mu value can be written as 8 sigma divided by 3 pi into RH. So, this will be the value of mobility if we consider the real case that the charged particles are moving in a random Brownian manner. So, we have seen already that for the n-type and the p-type material, the Hall voltage polarity will be changed. Hence, for n-type material, the Hall voltage Vh and the Hall coefficient Rh is always negative, and for p-type material, the Hall voltage Vh and the Hall coefficient Rh is taken as positive. For this n-type material, we can write the Rh will be equals to 1 by concentration of electrons, that is n, into the electronic charge. Similarly, for this p-type, we can write Rh is equals to 1 by concentration of holes inside the material into the electronic charge. Now, this Hall voltage Vh is very large for semiconductors. But in the metal, it will be very low, even it can become 0, because Vh Hall voltage is proportional to Rh, that is the Hall coefficient, and Hall coefficient is nothing but the 1 by sigma, and Rh is equals to 1 by rho, and rho is the charge density in the material, and we know that inside the material the charge density is very high, very high. So, this Rh value is low. So, the Vh value will be very low, and sometimes this Vh value inside the metal can become equals to 0. Similarly, for intrinsic material, it is found that the Hall voltage is equals to exactly 0. So, this is all about how the Hall voltage will be developed inside the semiconductor, and we have explained this using the Lorentz law and the cross product rule. So, this is all about the explanation of the Hall effect in the semiconductor. Thank you.